Welcome to the Ontario High School podcast. This is part 2 of quantitative problem solving for gaseous systems, pretty fancy name for how we solve problems having to do with gases when we vary their pressure, volume, temperature, or the number of moles of the gas. And the number of moles of the gas is how we're going to measure the amount, the number of gas particles involved. So, welcome. Let's take a look at a problem in which we're going to vary the pressure and determine what the new volume of the gas will be as a result. So what would be the new pressure if 125 cubic centimeters of a gas at standard pressure is compressed to a volume of 75 cubic centimeters? In this situation, temperature and the number of moles will remain constant. And when you see standard pressure is defined as 1 atmosphere or 760 millimeters of mercury. As always with any problem in chemistry or physics that we want to solve, it's good to have a data table. And the data table in this case is what we will call the IFE chart, the initial, final, and the change or effect that these conditions have. So we put our initial, final, and effect down the left-hand side of the table. Then our pressure, temperature, volume, and mole quantities go across the top. Our initial pressure is 1 atmosphere. The temperature stays the same, so we're not going to do anything with that. Our initial volume is 125 cubic centimeters, and our number of moles also remains unchanged, so we'll just put an X there because it's not going to affect what happens here. For our final pressure, we'll put our question mark. That's what we're trying to find. Again, our temperature, number of moles, just put an X there. And then our final volume is 75 cubic centimeters. We put a downward arrow representing the fact that the volume is decreasing. That's our change. And in the next slide, we'll see or evaluate what the effect of that change would be. In this situation, we have a volume decrease from 125 cubic centimeters to 75 cubic centimeters. We know that temperature and the number of moles of gas stays the same. We want to predict what will happen to our pressure. When we are relating pressure and volume at constant temperature and number of moles of gas, we're going to use Boyle's law to predict what that change will be. So one of the things that we talked about before is that pressure is related to the inverse of the volume with Boyle's law. Okay, the mathematical relationship is P is equal to or proportional to 1 over the volume, or the inverse of the volume. And because of that, if the volume has decreased, then the pressure has to have increased. So the effect prediction here is that we will put the upward arrow representing that pressure had to increase for this change in volume to occur. Since we've predicted that the pressure had to have increased for the volume to decrease, we're going to take the initial pressure and multiply it by the ratio of the volumes that would be greater than 1. So we will put our initial volume on top, our final volume on the bottom. So we have 1 atmosphere times the ratio of 125 cubic centimeters divided by 75 cubic centimeters. The cubic centimeters will cancel, and we get a final answer of 1.7 atmospheres. So again, the volume ratio set with the higher volume on top in the ratio, consistent with Boyle's law, that if volume decreases at a constant temperature and number of moles of gas, the pressure had to have increased. Let's look at a problem where we're going to change the amount of gas that's in the container. In this case, again, we measure the amount of gas in a quantity called the mole. So we have a closed flask that contains 2 moles of gas. The pressure gauge reads 212 kilopascals. What will the pressure gauge read if the amount of gas is increased to 5 moles? In this case, volume and temperature will remain constant. When we get to the next slide, we're going to look at the data table, but before we move on, why don't you pause the podcast and write your own IFE chart and make your prediction, and let's see how we do. Okay, let's compare your data table to mine. The initial pressure is 212 kilopascals. Our temperature and volume remain constant through this, so we're not going to put anything but an X in those boxes. Our number of moles initially is 2 moles. Our final number of moles is 5. And our final pressure, of course, has a question mark because that's what we're trying to find. Now, the effect of an increased number of moles on pressure, we have to look at the relationship of pressure is based on the collisions of particles with the walls of the container. The more gas particles there are, the more collisions there will be. So we would predict if the amount of gas, the number of moles of gas increases, then pressure would increase as well. So here's the final IFE chart. We have put our upward arrow into the effect on the pressure box because of that fact that an increased number of particles colliding with the walls of the container would bring in increased pressure in the container. We're now ready to set up our ratio of moles so that when we multiply that by the initial pressure, we'll get a pressure greater than our initial pressure. So the next slide will show that. We're ready now to solve. So we're going to take our initial pressure, multiply it by the mole ratio here, the ratio of the number of moles of gas, that is arranged in such a way that that ratio will be greater than 1 because our prediction of the effect on pressure is that it will increase. So our initial pressure of 212 kilopascals times a mole ratio of 5 moles over 2 moles. The moles cancel. We're left with 530 kilopascals as our final pressure. Please note the line over the 0 and the 530 indicating that that 0 is significant. So there are 3 significant figures in the answer. The larger final mole value is on top in the ratio, making sense that if there are more gas particles to collide with the walls of the flask at constant temperature and pressure, then pressure will increase. Let's go on to a more complex problem. This is a problem in which more than one of the variables that we look at in gases changes. So let's take a look. What would be the new volume if 425 milliliters of a gas at 20 degrees Celsius and 725 millimeters of mercury were changed to standard conditions of pressure and temperature? In this case, the number of moles of gas will remain constant. And again, please note, standard temperature and pressure is 273 Kelvin, 760 millimeters of mercury. Also note that 2 of the conditions change, so in this problem 2 ratios are needed to solve this. Now, if you will go ahead and make out the IFE chart, pause this, make your chart, and then come back when you're ready. Let's look at our IFE chart. Our initial pressure is 725 millimeters of mercury. Our final pressure is 760 millimeters of mercury. The effect of an increase in pressure, our initial temperature is 293 Kelvin, our final temperature is 273 Kelvin, and so our temperature has decreased, so we put an arrow in to reflect that. Now, we have to look at predicting what will happen to our volume based on the effects of both pressure and temperature, and you really need to treat those individually. Our number of moles of gas stays the same, so there's no effect due to that. Now, in this case, and this is a rather interesting case here, an increase in pressure, if we look at Boyle's law, would indicate that the volume should decrease. And so we would put a downward arrow. But before we put that downward arrow, we need to look at what the decrease in temperature will do. The decrease in temperature, according to Charles' law, will also yield a decrease in the volume. So we have kind of a happy congruence here between the changes in pressure and temperature, in that their effect on the volume will go in the same direction. Our happy congruence here is that an increase in pressure predicts a decrease in volume, and a decrease in temperature also predicts a decrease in volume. So we can easily just put a downward arrow in the volume box, knowing that both of these will act to decrease the volume. You may at some point see a problem where, let's say, your pressure increases, which would predict a decrease in volume, but your temperature increases, which would predict an increase in volume. In that case, split the effect box underneath the volume in half, and you would have two arrows there, one related to the change in pressure, one related to the change in temperature. You just use those predicted changes to arrange your ratios to make sure that they're lined up correctly. So if you need to split that, do so. But in this problem, you do not have to. So as we look at both of these predicting to decrease the volume, we know that we're going to use two ratios. The ratio of the pressures has to be arranged so that it's less than 1, because volume would decrease as a consequence of the increase in pressure. And the decrease in temperature also has to be arranged so that the ratio is less than 1, because a decrease in temperature also predicts a decrease in volume. Since two things change, two of the conditions change, we're going to multiply our initial volume amount by two ratios. The ratio of the pressures and the ratio of the temperatures, arranged so that each of those ratios is less than 1, leading to the end decrease in volume that we would predict. So our initial volume is going to be multiplied by the ratio of pressures that is less than 1, which is 725 millimeters of mercury divided by 760 millimeters of mercury, and also by a second ratio of temperatures that is less than 1, predicting our decrease in volume, with 273 Kelvin over 293 Kelvin. Our millimeters of mercury, our pressure unit, and our Kelvin, our temperature unit, both will cancel. And again, note that we do not use Celsius temperatures when we deal with gas laws, only Kelvin. So those units cancel, we're left with milliliters, and our 425 milliliters times these two ratios gives us a final volume of 378 milliliters. Increased pressure results in decreased volume, consistent with Boyle's law. Decreased temperature results in decreased volume, consistent with Charles' law. The smaller ratios of pressure and temperature, the smaller values of pressure and temperature are on top in the ratios, reflecting these realities of gas behavior. Thanks for watching this video podcast concerning gas law calculations from Ontario High School. I want to leave you with this thought from a great novelist, Mark Halperin. As long as you have life and breath, believe. Believe for those who cannot. Believe even if you have stopped believing. Believe for the sake of the dead, for love, to keep your heart beating. Believe. Never give up, never despair. Let no mystery confound you into the conclusion that mystery cannot be yours. I wish you well.